Oh my God. It's fine. I do my very best not to freak out when something like this happens. Just say no, you have recorded live on YouTube, and we can hear you. Ooh. But it looks good. Actually, I saw that you have a pool here. Maybe I should have stayed the night. Oh, I see the water slide. Yes, there's the water slide. And then you will fix it. Yeah, they will people to I'll work on that right now. It's more advanced, right? I have no R. No. She has no R. No R. Your lecture, right? Lecture, yeah. My first-day summer school. Ribana from the University of Bonn, from the Roscher group. So she's going to explain to us explainable AI. Yeah. Thanks. Yeah, thank you for the invitation. It's always nice to speak at the summer school. Yes, so a little bit to my content. So what I tell you today is explainable machine learning, but also based on what you have heard before, I will give an introduction to also to convolutional neural networks, because this is something what we need for later in the talk. So the first, let's say, 45 minutes is introduction to CNN, and then I switch over to explainable machine learning. And everything what you see, what I tell later, the methods for explainable machine learning can also be used, or most of the methods can also be used for other methods like random forest or something like this. Okay, so let's start. Yes. So I hope you can see everything, and I want to start with with an example, and that means typical questions we are concerned with in Earth observation data analysis. And all of the questions I show you now here have a different level of complexity and difficulty. So, for example, when we have Earth observation data, you can ask what is here, which is a classification task, or you can ask what is the biomass in a specific area, which is a regression task. That means you have a continuous output. Or you can ask what would it look like next month, which is a forecasting task. Or you can, yeah, all this kind of question which belong to the area of classification and regression. And such question can be approached with data science. And so data science is a field of study that uses scientific approaches to extract knowledge and insights from data. And one part of data science is machine learning, which is a set of techniques that allow computers to learn from data. And one part of machine learning is deep learning. So on the right, you can see, okay, no. Let me check if I can laser pointer. Good. Yes, perfect. So on the right, you can see a typical machine learning pipeline. So we have given some measurements. These measurements can be close range or satellite based, and we want to have a specific model output. And the machine learning model is simply put the mathematical relationship between the input and the output. And in order to learn this relationship, we need domain knowledge. That means we need reference data with input-output pairs. And once such a model is learned, we can apply to different but similar input data. But in many cases, we do not have, we do not only have to want the model output, but we want to have some scientific output. And then scientific outcome is can give us new knowledge or insights from data. I would talk a little bit more later what is the difference actually between a scientific outcome and a simple machine learning model outcome. Okay, so what I showed you until now were only what questions. So like what is here, but there are also other kind of questions we are interested in. For example, why does it look like this? Or why does my algorithm perform poorly here? Or how did my algorithm come to the conclusion that this is water? And these two kind of questions, the what and why, and the what question, the why and the how question, reflect also the two parts of my tutorial, of my lectures. So the first one will answer the what questions, which is specifically for convolutional neural networks, and then we will answer the why and the how question, which is the part of explainable machine learning. So, but first of all, let me give you a little bit more insights into deep neural networks for image interpretation. So what I heard is you already had some kind of introduction into machine learning and neural networks. So I want to specifically now focus on how can we use neural networks for images. But let me briefly summarize what you already should have heard, because the notation is always different, and when people they show it differently. So just that you know my notation. Okay, so what you have given here is a simple neural network. You have an input layer, you have some hidden layers and output layers, and all these colored dots are the neurons. And so the input layer is your observational data. The hidden layer are all layers which learn a new representation of the data, and the neurons are the function yielding the representation. Okay, I'm back. um,
Okay, so if you share your screen and just this one,
and
then here you can go back to your notes.
Okay. So, is this okay? Because okay, perfect. Good. So in Zoom you can see the normal screen. Okay, good. If not, please tell me. So where have I been? Yes, neural networks. So output layer. This is actually what you want, and yes, you can whatever you want to relate from the input and the output. For example, some parameters, and you want to have an image as output or an image as input and text as output. That's really nice, but there must, of course, be a relationship between the input and the output. Okay, so overall, a neural network is nothing else than a complex mathematical function which relates the input to the output. And this function can be seen here at the bottom. I need a laser pointer again. Yeah. Here. Yes. So this function represents a neural network. So y tilde is the output, and the output is computed with the function f depending on x. This is your input, and y is the vector of all weights which are computed in a network. And here one connection is one weight. And this function is a so-called nested function, because in a neural network you have a chain of operations, and here from the left to the right, that means the output from a previous layer is the input to the next layer. And W1 contains all weights connected to the first hidden layer, and W0 is the first hidden layer, and W1 contains the weight connected to the second hidden layer. And then you have F0 and F1, which are nonlinear functions, because an overall linear function would just not be complex enough and or not powerful enough for most of the tasks. And what I didn't, yeah, and then here are the weights, the biases, which add an additional scalar to each layer. And of course, you have the loss function, which is the function which you need to be optimized to get the parameters of the neural network. Okay, but that's just to that you know my notation. And let's come now to convolutional neural networks. So when we have a look at such complex scenes, here you can see agricultural fields in the desert of Saudi Arabia. So the neural networks I presented in the first few slides would just not help us. So, but convolutional neural networks can help us with this. So here you can see the how these agricultural fields look like, and they you can already see that they have nice patterns. And so let's have a look at the basic principle of convolutional neural network. So what it takes, you have an input image. It's a 2D array of pixels, or for example, a 3D array in case you have more than just one, not only gray value image, but RGB or multispectral. Then you have a 3D matrix, and then you have and just by looking at it, the CNN decides whether it's an agriculture area or desert. So you have two classes in this case. And when you look at the complete image, you see that there are a lot of round objects, but they can be translated, they can be scaled, rotated, or weighted. So they all look a little bit different, but they have a similar structure. And so some characteristic parts of the image are illustrated here. And I think you will agree with me that they are very similar. And the trick what convolutional neural networks use is they compare parts of the image rather than the whole thing. So they look for typical image patterns, parts of an image. And so a CNN tries to find typical structures which are similar in the image, and the mathematical operation which is used for it is convolution. It's also called filtering, but yeah, the mathematical operation is convolution. And what happens during a convolution is that a filter is compared with an image like illustrated here. So you have a filter given here, and you have an image, and this is what happens when you do when you perform a convolution. So you shift the filter over the image, and then you get such a feature map, also called activation map. So for the rest of the talk, I will maybe sometimes switch between feature map and activation map, but it's actually the same. So this is the output from an operation. So the feature map tells for each position how good the filter resembles the image, and that means we get an impression of how well the filter fits to specific parts in the image. And you can already see that, so the darker parts, there's not much similarity between the filter and the image, and where you have such peaks, that is a very high similarity, and you can actually see the peaks of the agriculture fields. So the whole convolution is then repeated with other filters. This is exactly what is happening in a convolutional layer. So you do not only have one filter, you have multiple filters. And in each case, we get a feature map. And the sign here, when you see this in papers about neural networks, the sign is exactly shows this a convolution is performed. So it's a short-term notation for a convolution. And these feature maps are stacked together and creating a stack of filtered images, which is the output of the convolutional filter. And these are all feature maps or activation maps. And a very important thing to mention is that the filters are learned. So it's not that we say what are good filters, what are the patterns to search in a neural network. The filters are learned. That's why convolutional neural networks have mostly a lot of parameters, because each of the filter already has a lot of parameters, and then you have the connections, so even more parameters. And yeah, so we do not have a few filters or a convolutional layer in convolutional neural networks. We have a whole convolutional neural networks where we have, so we have not only one layer, but we have multiple layers. So we have an image, then we perform convolution with multiple filters. And then the output, these activation maps, are fed into the next convolutional layer and are convoluted again and again. So it's a convolution of a convolution of a convolution. This nested function, which I mentioned before. And the very nice thing is that because it's the chain of operation, neural network or convolutional neural network is able to learn very complex features. So in the first layers, you normally find patterns like edges in the filters, and later very complex structures. But we'll tell a little bit more, because there are some tricks where you actually can force the network to give you nice complex features in deeper layers. Okay, so let's go back to our example where we want to have a decision about an agriculture area and desert, so class 1 and class 2. And in order to get such a decision, we introduce a fully connected layer, which is illustrated here. So here, every value gets a vote on what the answer is to be. And the vote is the weight, which is learned. So you have the feature maps here. And then you perform a flattening operation. Flattening, if you're familiar with MATLAB, it's the vec operator, the vectorizing. But here it's in neural network community, it's called flattening. And each feature value gets one vote for each class. So you flatten them, and then each value gets a weight. Of course, you can apply here nonlinear activation to get scores between, for example, 0 and 1, which is sometimes really good, because you do not only want to have an arbitrary output for a decision, but if you have for example, a value between 0 and 1, you can interpret it as some kind of probability or score. It's better comparable, and it has really nice properties. And again, what is done here in the first part, I mentioned it already, this is the representation learning part. So in this part of the neural network, before the decision is performed, a good representation is learned. So the filters give you a good impression about what good patterns, important patterns in a neural network are. So the question is now, how can we pixelwise segment the image? So what I showed you before was a scene classification. So you had one image or one patch, and you get one class for one scene, which is sometimes okay, but sometimes you really want to know for each pixel which class it belonged to. So yeah. And the first possibility is a sliding window categorization. So what you do here is you take your input image and break it up into many, many patches, actually overlapping patches or right next to each other. And for each patch, you learn a neural network. That's possible, and then for each patch, you do perform scene classification. But as you can imagine, that's actually very computational intense. And the disadvantage is also that you need to have a separate network for each of the patches. So you have you learn actually, if you have overlapping patches, you learn similar things, because if you shift it a little bit, you already did with the you were dealing with one part of the patch, and so you already learned these patterns. So it's just super inefficient. So yeah, in the end, it's a bad idea. So don't do this. It works, but don't do it. There are better possibilities, like the second one. So the second possibility is to design a network as a bunch of convolutional layers to make predictions for all pixels at once. So what you can see here is the input image, height, weight, and in this case we have RGB. That's why we have 3 dimensions, where we perform a convolution and again and again and again. And in the end, you have operations where we have scores. And so here we determine scores which have exact dimension of the image, like the height times the weight times C, and C is the number of classes. Yeah, so first of all, this is also computationally expensive, better than the first solution, but not really good. And in order to capture different sizes of patterns, you need to think about different filter sizes in these layers. So when I told you that the filters are not that they are learned and not set manually, I also meant in the best case, you also do not want to think about what patterns or what size of patterns should the network be extract. So the network should figure it out on its own. So overall, this is also not a good idea, but these were the first solutions to neural networks. But now we have better approaches. Like the third one. And so instead, yeah, here's the better choice of networks, which look like this structure here. And this is the structure you will find in my talk and also in a lot of papers all over, because it's a very, it turned out that this is a very, very good structure for networks. So instead of doing the convolutions on feature maps, having the whole size of the image, we use smaller feature maps. And the concept, so what we use here is the concept of downsampling and upsampling. So downsampling operations are, for example, performed here, and upsampling operations are performed here. The concept behind downsampling is that you summarize information in a specific area. So you make the current representation more compact, and also you only focus on the important information. So every time you compress something and it's learned, the compression learns only the relevant information, hopefully. But in a lot of cases it does. So, but if you don't sample, you need to upsample again, because in the end, of course, you want to have an output which is of the same size as the input. So for each pixel, you want to have a decision. So this downsampling strategy is called encoder, and the second part is called decoder. So in the encoder, you compress the data to a low dimensional space. It can also be seen as a very smart dimensionality reduction. And then you upsample so that in the end you get a result which is of the same size as the input. So why exactly, I already mentioned it a little bit, but why exactly should we downsample? First of all, it reduces the complexity. That means you have less parameters in the network. So if you have these huge images, you need more parameters to represent everything. And also imagine you would need filters of different sizes and so on. So this approach reduces the complexity. And second, if the convolutional filter size stays the same, this downsampling layers cause an increase in the receptive field in deeper layers. Okay, what does it mean? First, here, the receptive field is the region in the input which produces the feature. So if you have a filter and put it on an image, this is exactly the receptive field, because this is where the operation takes part and what the filter sees. And here you can see stacked feature maps, activation maps of different sizes. And if the filter size stays the same, you can see that the receptive field it's much larger. So here, imagine you have such an activation map or feature map of this size, and here of a smaller size. If the filter stays the same, here you extract actually small features. And if it's downsampled and the filter size stays the same, it extracts larger features. And this is where it's happening, that you extract patterns of different sizes, actually due to the downsampling. So very smart. So what is done very often is that the number of filters increase with the depth in the encoder. So this is illustrated here. So in the very beginning, you start with a few filters. Let's say you start with 16 filters. And normally what is done is you double the size of the filters in the next layer, and then you double again. So it's increased all the time. This is mainly due to two reasons. First, generally, so the lower layers with or in the first layer, as I said, mostly simple features are extracted. So filter normally act as an edge detector, or something like this, and they work for all classes. But high-level concepts and deeper layers don't work for all classes. So in the early beginning, edges, you don't actually need not so many filters. But for the later concepts, where you also want to learn specific patterns for specific classes, you need more filters because they are more complex. And also, that means the correlation between the filters decreases with the depth. So in the beginning, if you have edges, if you have too many filters, they might be too correlated. And generally, also the architecture is chosen to be in a symmetric way. So if you choose the downsampling structure, you actually have the upsampling operations in a symmetric way. And I will talk about this in a little bit more. So what are actually symmetric operations? What does it mean when I downsample and with a specific operation, what is the actual symmetric upsampling procedure for it? Okay, and also if you have questions, please interrupt me all the time. I'm happy to answer questions. Yeah.
So the difference of in the first layer, you have the old information, and then next is the most important features, and
Yes.
And then we find.
Right. So because for me, it always helps to think of, because we are optimizing the network. So you have input-output pairs. The network really tries to find the important patterns which are necessary to classify a specific image. That's why it's so hard to train neural networks, or it can be hard to train neural networks, and why they have so many parameters, because the filters and so on, they all have parameters and they're actually tailored to specific application. And but I think it will get a little bit more clear when I show exactly what operations can be performed. But yes, that's the general idea behind it. Yeah, so one example for downsampling and upsampling is pooling. So pooling is an easy operation. There are also other ways to do this, but this is the easiest one and also a very commonly one. So let's have a look at pooling and what does it actually mean. So pooling generally means that the information is fused, so the image stack is shrinking, so it's downsampled. And the most commonly used procedure is max pooling, but there's also mean pooling. And I will show you the operation here, what actually happening when you perform max pooling. So pooling is a relative straightforward operation. We pick here, you have an, let's say, a feature map illustrated with some values here illustrated in light and dark gray values, for example. And we pick a window size of 2 × 2 here. And then we pick a so-called stride. And the stride is defining how much the window is moved from one operation to the next one. And we walk, what we do is for pooling, like as the same for convolution, we walk the window across the filtered image, and from each window we take the maximum value. So here, for example, imagine the light pixels illustrate high values and dark ones denote low values. Then from this window, the highest value is the white one. And then you move it with a stride of 2 in this case. So you hop 2 pixels to the right. And you again take the maximum value, and then you're at the border. But that doesn't matter. You just take all the values into account which are actually in this window, and again you take the maximum and you do it for the whole patch. And you can see now it's downsampled, and you summarize the information with the maximum operation. And so if you have really large images with thousands of pixels, this is a very convenient way to shrink the size. And the good thing is pooling doesn't include parameters. So here you can save parameters. And if you do not have enough time for computation, you can speed it up a little bit. Okay. Yeah, actually, what is interesting here, maybe you cannot see it that good, but here's a diagonal feature with high values, and this is actually, you can also see in the smaller patch. So the actual patterns are stored, they're still there, and it's not destroyed by the pooling. And then, yes, you need the upsampling strategy, and it's called unpooling. So you have pooling and unpooling. And there are different strategies. And again, here, let's say you have a 2 × 2 receptive field, and you want to have an output, you want to go back to 4 × 4. For the nearest neighbor, you just, as you can see, you just choose, the value of the nearest neighbor, and you just increase it, which is, it reminds a little bit of interpolation strategies. And there's also like, for example, the bed of nails. This looks like, like a bed of nails. That's why it's called like this, because you have a flat region with zeros, and then the other values are like poking up there. So everywhere you don't know anything, you just fill it by 0. Or if you do there's another strategy where you keep in mind where the maximum values at which positions they were, and then you you use it for the unpooling again to place them there. Yeah, so that's the pooling and the unpooling. So I mentioned now one operation, but it's not only that the convolutional neural network has only convolutions and pooling operation, it has generally way more operation, and they're called stacked layers, and sometimes they're illustrated in such blocks here. So what is a typical sequence in convolutional neural networks is so that you have convolutions and pooling, or you have, for example, operations like here. So I have blocks of convolution, then you have some kind of normalization, then you have an activation function, or for example, you have a max pooling, then convolution, normalization, and activation. And this is repeated all the time. And if you go to the literature and you have a look at CNN architectures, you will find there is very similar. So it's not that they, with each new architecture, the whole neural network is invented from scratch and invented new. It's you find some some procedures how to stack filters all the time. And here, so one example of a network which I use very often for image segmentation. And you can see that it's really not that big, but it performs really well. These are actually X-ray images from soil, and we want to find debris in it. Okay, so this is the principle. One thing I want to mention is here, you cannot only downsample and upsample with pooling. One procedure which is also used very often is that you use convolutions as a downsampling strategy. This is done when you use a stride of 2. So every time you do not have a sliding window approach with the convolution where you have only move it 1 per operation, but you jump for 2 pixels. And so it's also shrinked. This includes parameters, but it causes, or sometimes it can happen that you a pooling is not strong enough, and you better use a convolution for downsampling. And in this case, these networks are called all convolutional neural networks. Okay, what do you need to learn? What I said already, you need to learn the filters. Then you need to learn the weights in a fully connected and dense layer, so for the final decision. But if you use pooling layers, there are no parameters included. So how is it done? This is done backpropagation. I don't know if you already heard about it in the summer school, but if not, backpropagation is just a very smart way, a very efficient way to determine the parameters in the neural network. So it's uses gradient descent as optimization strategy, and so the weights in the network are updated in a really nice way. And it's called backpropagation because you perform a forward propagation to get the current estimation with the current weights, and then you perform a backpropagation by updating the weights in the network from the back to the front. And there are also some hyperparameters. So hyperparameters are always parameters which are not define actually, for example, the decision boundary, but they influence the result in some way. And some hyperparameters which need to be set is the number of filters. For example, you say in the beginning you want to have 16 filters, and then you want to double it, or you want to start with 32. Then the size of the filters, it turned out that it's really good to start with a very small filter. So do not start with big filters, but small filters, because when you downsample, the more complex features are extracted anyway in the deeper layers, and then you have a larger receptive field. And also you need to decide on the window stride. That's means how much you downsample, how fast you downsample, and how fast you upsample. And for pooling, also you need to decide on the window size and the stride. So one thing I want to mention here is that the hyperparameter tuning can be a really tedious process, and so it's really nice that the neural networks now we do not need to manually handcraft features anymore, but so the effort is taken away, but now the effort needs to be put in the hyperparameter tuning. So this is, I see it as a shift, just that you with, for example, with random forest or some other methods beside neural network, you need to think about which features you need were fed in, but now you need to think about the hyperparameters. And last thing I want to mention here, as for this introduction, before I start with the explainability part, is pre-trained networks, because I think it's a really important topic. So pre-trained networks is it's a very smart initialization of neural networks. So it's not that you design a neural network architecture every time you want to solve a task, every time you have an application. There are some good architectures out there which can be adapted and changed a little bit. And for them, they are good initialization. So you do not need to, you don't need to start the optimization process from scratch, which can be, which can cause a very long training procedure, a very long optimization procedure. And pre-trained networks is, for example, you use a network, which you also want on natural images. So something already was done with the network, for example, image classification on ImageNet or some handwritten digits, something like this. And then you take the network with the weights and you fine tune it on your data. So you already have a good initialization. And although the data might not be still, it's a good solution because images still have a similar structure. So it's not that it has some random effects in there. So images are still patterns, and they have all similar patterns. However, different is different possibilities how you can use a pre-trained network. So you have an input, then you have the feature learning part, which is the representation learning part, and then you have the task solver. That means the decision layer for classification or for regression, and then you have an output. So green means that this unit on your data, and white means that this part is fixed. So different possibilities are that you retrain the whole network. So you can, for example, use your pre-trained network and then you fine tune everything, or you fix. Not that I need to update the weight, and I retrain it. Or the whole learning process. What you need to consider is the number of late examples and how many samples you have in your class. How similar is this data to Oh yeah, sure.
are there any kind of studies how different the weights are depending on different training data sets?
Yes.
So say I train on English languages and I
Mhm.
train on data sets like kind of planes, cars, buses, whatever.
Yeah.
So how different will the weights be? And put it the other way around, is there the width they use pre-trained model, but then miss my important features because I use the model?
Yes, there are not really, there are studies where they took specific pre-trained networks and they tested how much they change on like remote sensing images. There are works there. I cannot remember which paper it was, but it was really nice because they did a comprehensive study and turned out that this huge ImageNet data set, which is very often used for pre-training networks, is already quite good. So you can use it as a good basis. But from my experience, this can change very fast. So it happened to me that I think, okay, the data is not that different, and the weights changed a lot, or the ImageNet pre-trained data didn't work at all. So I cannot give you a rule of thumb. I think it's just you need to do some initial studies and see. Also, I think one problem in quantifying how much the weights change is that you have so many weights that there's no unique solution and how the weights can be arranged to find to solve your task. So and also when you think about okay, so when you think about possible solution for neural networks, I always think about this loss landscape. So actually this landscape, this high dimensional landscape of the loss, where you want to find a minimum. And it's not that you have one good, best minimum, maybe. There are a lot of local optimums which are good, which are as equally good. This is what they found out a few years ago, that you doesn't need to search, or you don't need to search for the global optimum. It's local optimum are very often also as good, and they can have a very different constellation of weights. But it's I imagine it, or I think of that your pre-trained network is a starting point in the loss landscape, and then you go to, let's say, the next local optimum. But maybe there's also another pre-trained network which would also lead to a good solution.
It depends kind of how complex this loss landscape might
Yeah.
be, where this call I might find the point.
Yes.
Or might not. Kind of connected question maybe towards cooling. You showed the example the max cooling. Just using mean values, also approaches means that think about kind of introducing like spatial weights. So depending how far my cooling mass is away from the center, I find the weights different.
Yeah.
Pixels.
There are a lot of possibilities. I mean, if you do not want to think about it, you just use convolutional downsampling, then it's learned. Maybe there are some patterns that you should give more weight in the center and less weight to the edge. I don't know. This is actually one thing you could do with explainable machine learning, because then you can look into it and look what filters are learned. Unfortunately, I will not show this, but I just want to mention that it's possible that you can do it.
Can you use some pre-trained data from, let's say, a grayscale image also to use it on an RGB
Yes.
data? Or do you have some requirements in terms of what your input data structure is like, and what your model also like the dimensions of it?
No, I mean, what you can do is, as I showed here, you can just keep the middle part of the network, and you just replace the very first layer, which would be the grayscale image, or you can duplicate it as grayscale, as RGB. This there are some works who do exactly this. They to summarize it, so what you need to consider is the number of labeled samples you have, which is in remote sensing very often not a lot. And yeah, the data similarity between your data and the pre-trained network. And on the upper left, you can see it's recommended to train the entire model when you have a large data set, when you have a lot of data available, but different from the pre-trained models data set. So you can use it as a good initialization, but fine-tune the whole network. Then here, the upper right, you train some layers, which would actually be exactly what you asked, and leave the others frozen, like the very first. And so this can be done when you have a large data set and similar to the pre-trained models. And so on the bottom left, you train some layers and leave the others frozen again. But this is done when you have a small data set in different, from the pre-trained models data set. So if you do not have a lot of available data. And again, when you have a small data set similar to the pre-trained models data set, you freeze a lot and you only retrain or fine-tune the decision layer. Mm-hmm.
So the are solved for classification task. If you want to fine-tune a task like segmentation and everything, that is for the same principle.
You mean when you want to change the task?
Yeah, because the pre-trained one will be on classification.
Yeah.
And the last ones are mostly like pro to the task thing.
Yes.
I want to move to a task called segmentation task.
Mm-hmm.
Which is like quite different than pre-trained task, despite everything else is similar.
Mm-hmm.
So how the strategy goes there?
Okay, so this is actually the principle what is done in the so-called self-supervised learning currently. So what you do there is you replace the very last layer. So self-supervised learning is when you have, let's say you have a few labels and you have not enough to train a whole network, but what you can do is you can define pseudo labels. So for example, you have an input image and you have pseudo label that you rotate your image, and the network should classify if the image was the original one or rotated one, or you change the spectral something, and the network should decide if the spectral values would change. So this is a task you pre-train on. So you don't need other kind of data. You use the data what you already have, and then you cut off the very last layers and you use a new layer for your actual task. So this can be done. Of course, you assume that you use the same network. So if your architecture change, then it's nothing what you can do.
My question is more into like fine-tuning or transfer. Like how do we go? Like how much do we fix the previous like initial layer?
That's a good question. I don't think that there's a rule of thumb. Maybe there is one, but I don't know. I'm always skeptical with rules of thumb which were made in a specific community and if they really apply to remote sensing community. So what I heard is that it sometimes can be enough just to cut off the decision layer and everything works. But I think I already heard the same amount of applications where it didn't work. Yeah, that's always. I mean, I had already some talks and lectures and summer school talks, and it's always the same question. So so are there rules of thumb? Can you give some hints how to choose something? And I always need to say of course there is something, but it totally depends on the application. I know it's not really satisfying when you say it depends, but it's like this. But that's also why it's so challenging and it's not only we take a network and we apply it to our data and it works. So this is what some people think. I know, I also need to deal with it. It's challenging. Yes, so to sum up, for the first part, so convolutional neural networks are suitable to extract structural features. This can not only be done in the spatial domain, but also in the temporal domain. So you can also define the convolution over time. So over time series, so you learn patterns in the time scale. And it's commonly used for gridded data, but it can also be used for graph. And then you define, these are graph CNNs, and then the convolution is defined on a graph. So this also works. And convolutions can be combined with other networks, for example, convolutional autoencoder. An autoencoder is a network where the network tries to reconstruct the input. This can be, for example, done when you want to perform dimensionality reduction, or you want to learn the really important features of your data, which can be found in this bottleneck layer, which is the smallest layer in the middle. Okay, so that's the first part, and I think it's 10, so I have another half an hour to start with the explainable machine learning part. That's perfect timing. And I need to change the presentation because I hope I will not. Oh, where's the, where did you copy? Sorry. There. Oh, I can see myself. Okay. Here.
On the left. Oh, there's no.
Oops. Okay. Oops. Okay, and I think I need to share my screen again. Here, just one.
And now you can go in presenter mode. Yes. This one, this is the first one, right? It's the same?
Yeah, okay. That's so.
Okay.
Okay. Yeah, this is shared. It's now shared in Zoom. Okay, good. So yeah, I want to continue with the second part of my talk, which is focused on explainable machine learning. And I want to start exactly where I also started in the first part, which is these why questions. So just to remind you, what I said is we have sometimes not only the what question, but also the why and the how question. So for example, why does it look like this? Or why does my algorithm perform poorly here? Or how did my algorithm come to the conclusion that this is water? And so first of all, let me summarize briefly what I mean with explainable machine learning, because there's no common sense or no common understanding in the community. But yeah, so this is what I tell you today is my view on explainable machine learning, but don't be surprised if you read other papers that they might differ a little bit. So when we approach a specific task like instance segmentation, like here, we can use deep neural networks, as mentioned before, which is nothing else than this complex chain of mathematical operations which relate the input to the output. But these networks, as mentioned before, are quite complex. So it seems that deep neural networks are the prime examples of black box models. And to make deep neural networks more understandable and to answer these why and the how questions, there are three core elements which need to be considered. And these core elements are transparency, interpretability, and explainability. So we very often talk about black box models, but mostly we actually have transparent models. So black box is the opposite of transparent. And so what does it mean, transparency? Transparency of a machine learning approach concerns is different ingredients, such as the overall model structure or the individual model components or the learning algorithms. How was the network or this machine learning model trained? Or even how the specific solution is obtained by the algorithm or the motivation why a specific algorithm was used. So this is all related to transparency, or what would be interesting to know. So quite often we have access to some of these components, and also for deep learning models, you can actually see here as one example, as in many cases, you can even write down the equation. It's complex, but you can write down the equation. So it's actually not, the laser point again. So actually, it's not a black box model. The problem is not the transparency. It's more that the model is too complex to be understandable. And this is what interpretability is concerned with. So interpretability is about making sense of the obtained machine learning model with the aim to present some properties in understandable terms to a human, such as feature statistics, such as feature importance. I think this is something you already know from decision trees, random forests, or maybe also linear models where you have a look at the weights. Or you can have data point with special significance, such as archetypes or prototypes. Archetypes are the extreme points of a data distribution, and prototypes are representative points like the mean or the median. And then some properties can also concern the model parameters, so that we want to have them in an understandable way, or patterns in the model decision process. And so the most prominent example for visualization, I see it as the most prominent example, are heat maps. And I think you already have seen some of them somewhere. And they can, for example, indicate why these images here are identified as the same whale. So these are whale flukes. This is a whale fluke, different photographs taken by tourists. And this is actually the same whale. And heat maps can indicate that this part here in the upper right corner is important for the network to decide that this is actually the same whale. So they visualize what the machine learning model based its decision on. But interpretability is not enough. If you listen carefully, I said, yeah, here in the corner, there's a hotspot, but it's not enough, because what you need is explainability. So research into explainable machine learning is widely recognized as important. And this is also a good sign that you are sitting here and interested in the topic, but there's no joint understanding of the concept of explainability. So it still needs to evolve, and I hope at some point the community gets to consensus about it. And so there's one important work which I want to mention here, the one from Adadi and Barada from 2018. And they mention essentially 4 reasons to seek explanations. So the first one is to justify decision. So we want to have an explanation. This is especially important when a decision is unexpected. So if you know why this decision was made, you could justify, for example, that it's fair and reasonable, and so you can increase the trust. Another reason is that you want to enhance control. That means explainability can help here to prevent that things go wrong. And if we can understand where the flaws in our machine learning models are and how exactly a machine learning model works in the way which parts are responsible, for example, a specific feature weighing or similar things, we have a better control over our model, and we can even correct errors, hopefully. So then another reason is to improve models. This is closely connected to the second one, but here, for example, when you know how your machine learning model works, and you know in which cases it will fail, it's much easier to improve the model. Otherwise, it might be unclear if it's the model or the data. I think we have been all in the situation that you are sitting in front of a program and you don't know if if your data is just bad or not as you wish it is, or if it's your model. So this helps you to find actually where does it come from that it's not working. And the fourth one is to discover new knowledge. So it's not only that we can machine learning use to align with our given domain knowledge or our given knowledge, what we already have. It can help also to find get novel insights into the data. And this is actually the one thing I'm most interested in, and also where I focus my research on. So how can machine learning help to find something new in your data? And so the typical question relevant for remote sensing would be, for example, why a certain sample, or let's say an image or a pattern, has been classified in a specific way, or how would a perfect sample look like to be classified as class 1 or class 2? This would be, for example, a prototype. Yes, but I already mentioned interpretability is not enough. We also need explainability. And to make this a little bit more clear, so for a large part of the literature, there's no clear distinction between interpretation and explanation. But my co-authors and I, we came up with a distinction which is especially important in the sciences. So interpretability is when you present some properties of a machine learning model in understandable terms to a human. Explainability is when you combine these interpretable entities with domain knowledge and an analysis goal. So the reason why we distinguish between interpretation and explanation is that an explanation can change depending on the use case. That means the added domain knowledge. If you have an interpretation like this heat map, and I tell you this part in the image is important, where expert might have another explanation for it than a lay person. Something like this. Okay, so be careful, in literature is mostly not distinguished, but I think it's useful to do it. And so let me give you a specific example of an interpretation and an explanation. Let's come back here to this whale example. An interpretation would be, for example, the score for whale ID XY is significantly influenced by the image pattern in the right upper corner of the image set. And an explanation would be the notch in the fluke of the whale with ID XY is a relevant fluke pattern for identifying the specific whale. So on the bottom for the explanation, you have the added domain knowledge. And this is something where we need to really be careful, because there is a connection to correlation and causation. So when you think about it more deeply, it's clear that there is a connection when you think about interpretation, explanation, and correlation and causation. So causation means that an output is the result of the occurrence of a specific input, so that the cause and the effect. So the input is the cause and the output is the effect. Correlation measures the relationship between the input and the output, but it does not imply causation. To give you an example, it rains. So as a result, plants are growing, and I will use an umbrella. Although there is a correlation between the plants are growing and I use an umbrella, it does not imply that plants grow when I use an umbrella. And this is actually, so very often machine learning models focus on these relationships. And so when we connect this to the area of explainable machine learning, we will realize that the interpretation tools generally built on correlation, because an interpretation tool presents properties of a machine learning model, and this very often only captures the correlation between the input and the output. So here is the network, which is fine, which is, if you do not want to have a discourse effect, it's totally fine to learn a machine learning model to do this. And so there's nothing bad about it. So one thing we really need to take care of is the confirmation bias when we deal with interpretation explanation. The confirmation bias is the underlying tendency to search for explanations which are in line with our existing knowledge. So we might tend to explain something which we think we discovered, but it's actually not in the data on the model. So it very often, I see it very often in papers. I review or I just read that they made some conclusions from heat maps, but it might be there, but it might also be not there. So it's, in the end, the authors were just happy to see something which they think is there because it's they were hoping for it. And when you really want to see something in the data, you find a way to see it. So be careful, please, with it, and really check if it's in your data or not. So let me show you a quite obvious example where an explanation would be wrong because the model just captured a correlation, but not really a cause and effect. And this is one really nice example where explainability, explainable machine learning helps you. So here, a classifier was trained on various training samples, for example, on horses, on cars. And for some reason, there were a few images here which were classified as horse, for example, this year, with a very high accuracy. And that was just not reasonable because there's clearly a car in the image. So they used, in this approach, they used heat mapping, and it turned out that all training samples with horse tag in the image here. There was a tag only for the horses, but all horses. And the classifier learned that all images with the tag is classified as horse. And after the tag was removed, the images were correctly classified here. And this is a prominent example for a so-called Clever Hans effect. Clever Hans was a horse, not related to this, just coincident, it was a horse. And there was a story that Clever Hans was assumed to, that he can calculate with numbers, but in the end, his owner, or the owner of the horse, well, when he presented something to an audience and said, my horse can calculate and add numbers, and so he was so hoping he was pointing on numbers, and he was so hoping for the right result that he did some expression in the image, that the horse just realized when his owner did something, so he was pointing to the right result. That's why it's called Clever Hans effect. It is the right decision, but for the wrong reasons. Okay, so let's get a little bit more into detail. So when you think of how machine learning models could reveal insights into the decision process, you can categorize it by specificity. So the first one here on the top is when you explain the output by the input. This is a post hoc method and model agnostic. So the first one is that, so here you want to understand how the model relates the input to the output. And in this case, actually, you don't need access to the model. So it can be, that means model agnostic. You don't need to see the model, or you don't need, you need to access it so that you can produce a result, but it's not that you need to see the model. So in this case, actually, you don't care about the transparency. You just want to understand the mapping. That means what will happen to the output if you change the input. And then the second one is that you want to understand how specific parts of a network are responsible for a specific decision. So here, here you want to have interpretations through methods that were tailored to specific methods. So when you want to explain the whole model or model parts, it's model specific, and mostly these methods are specifically for architectures or even to specific model types. So for example, you want to have a look at the weights in the linear model. But then there's another distinction we can make. You can categorize it by locality. And so the first one is here, when you explain locally. Here you explain an individual output. That means a specific decision. This will give you insight about a characteristic of one specific sample. So that means locally. The second one is when you explain the whole model behavior. That means for all data samples. So you use the whole data set. And this can be done, for example, by calculating a prototype, which is a maybe synthetic, a typical sample, which will lead to a maximum score. And this helps to understand when your model will perform really good, which is when you have a data point close to your prototype or similar to your prototype. And you can also derive insights when it would fail. And then there's another type of approach, I didn't mention it here explicitly, which is the interpretation of the algorithm. So how does a specific type of model come to result? For example, as I mentioned before, in the first part, CNNs learn the first basic features such as edges, and deeper later, they learn more complex features. So you actually have a transparency, or you understand why specific decisions are made in this type of model. It doesn't have to do with specific data points or specific model. So the actual question is now, can explainable machine learning help us in remote sensing? And the answer is yes, of course, otherwise I would not do it. So it can help to tackle typical challenges which occur in remote sensing, but of course, these challenges also apply to other scientific areas. So what you can see here is, again, the typical machine learning pipeline. You have the input data, your model, and the output results. And so each part has its challenges. And so first is, the first challenge here is that the data is complex. And explainable machine learning can help here, for example, to point you to relevant patterns or relevant features. And generally, since interpretation helps to also to visualize these complex processes in a machine learning model, it helps also to understand your data with respect to the model and the tasks you want to solve. So this is also sometimes known as explanatory data analysis. So where it's always good not to start right away with the learning a machine learning model, but first have a look at your data, visualize it, get an impression about it, and then start with it. So the second challenge is that you want to handle limited training data. This is also what I already mentioned, especially in the context of neural networks who need a lot of data. So, so we need to handle a limited amount of training data. The reason is, of course, we know that we generally need experts to label the data, and this is a super time-consuming process. So the existing data we label should be correct, but also informative. You do not want to label everything, but you want actually only to label data which can be helpful. And here, explainable machine learning can help during the data collection process. So for example, by checking if the machine learning model makes the right decisions on wrong reasons. If you find a clever Hans effect in your current data, you know what, how, or what kind of data you need to collect to actually correct this clever Hans effect. The third challenge is that as soon as we use complex models such as deep neural networks, it is hard to understand what happens inside. That's what I said. It's hard to grasp what's going on. So it's a kind of a black box behavior. So many of the pre-trained networks are made for RGB images or point clouds with man-made objects and not really tailored to remote sensing images. And very often it happens that these networks are not suitable for remote sensing applications without adapting them. So we need to train them from scratch. So we cannot use a pre-trained model. It happens. And training from scratch can be a really tedious process. So if we understand the models better, it's easier to train them. So for example, if we would know when our network fails, we can think about how we can fix it. So just get a better impression. So in which part of your network something goes wrong. It's better than just have a black box and just see what will happen if you change something. I mean, we all have been there. And the last challenge is that you want to have a scientific result. So when we look at the output results, an important point is that the result does not necessarily mean that it's useful from a scientific point of view. This is something what happens a lot in machine learning, computer vision papers, which is okay, but they stop at the model output. But in our community, or if you go to any kind of the sciences, you need a scientific outcome. So it's even more. So what does a result makes more scientific? It's scientific if it's reliable and explainable. So you get, so you really can say, okay, this is happening because A and B. And when it's scientifically consistent, this is a different research area here. This is so-called informed machine learning or theory-guided machine learning, physics-guided machine learning. There are a lot of names. This is when you ensure that it makes that your result makes sense from a scientific point of view, that it or that it follows some physical laws or something like this. This is not what I want to talk about today, but it's clearly connected to explainability. Yeah, there's definitely an overlap. Okay, I would say, so the next part is methods and application. I would just, I would say I will give, I will shortly show what I want, which kind of applications I will show you, and then we can make a break, I would say. Okay, so first of all, what I mentioned before, I show you what kind of application I will show. There are several terms connected to interpretability. This is clearly a research area which is still developed. So researchers and users use different kind of terms and maybe mean the same, maybe mean something different. So I just listed here a few terms which are connected, for example, the contribution or importance, relevance, sensitivity, influence. This is just the first terms which came to my mind. There are a lot more. And what I want to say here, be careful what you really want, what you want to have, and if it fits your analysis goal, and what the methods do. So sensitivity, for example, will tell you what will happen if to the output if you slightly change the input. But and this is contrary to contribution. So contribution is the actual quantification of how much a specific pattern influenced the result. And you can see it a little bit like a mean and a standard deviation. So one thing is the contribution, and the other thing just gives you a variance, just a sensitivity. So, but sensitivity doesn't necessarily mean that it's actually an important feature or that it's actually have a high impact. So be careful. I will present different methods. One will give you sensitivity, the others will give you contribution. I just want to mention it here. And yes, so remember when I said there were a few reasons to seek explanation, I categorized the applications I want to show and categorized regarding these explanation. I want to focus on the reasons to seek explanation, and I focused on two. The one is to justify decisions, and the other one is to discover knowledge. And here I want to show you an example from whale monitoring, and I want to also show you a work where we focus on also on value estimation. This is a work together with Scarlett, and I'm happy if I say something wrong about ozone. It's good that you can correct me here, because I'm clearly not an expert in this application area. And for this discovering knowledge, I will show you how explainable machine learning can help us to understand wilderness, which is a land cover class which is not clearly defined yet. And before I go into details, I will present the occlusion sensitivity maps, class activation maps, and GradCam. I will explain Shapley values, and I will also show you activation space occlusion sensitivity, which is when you use occlusion sensitivity maps, but inside the network. Okay, I think then I would start with the whale monitoring, but first we can make a break and I can get a coffee. That's also nice. Okay, thanks a lot for the first part, for listening, and
so we just reverse at 11, so 5 people away.
also good. Yeah, works.
Sometimes also coffee should be prepared outside.
Should I mute myself?